Welcome. In this mini lecture, we're going to cover the key idea of Chapter 8, Proofs Involving Sets. The first thing we want to recall is the definition of a subset. We say that A is a subset of B if and only if we have that A is an element of the set A, then A is also a element of the set B. Note, this definition hinges on this piece right here. It's an if-then statement. So we want to make sure we keep that in the back of our mind. So in general, our proofs will look something like this. If we're trying to prove that A is a subset of B, we're going to choose an element X that lives in the set A. We're going to use some definitions until we can find and determine that X is also an element of the set B. Then, since A is an element of A implies that A is also an element of B, it follows that A must be a subset of B. And that's that definition above. It's a conditional statement that's part of our definition. So, let's look at a more complex example. We're going to let A and B be natural numbers, and we're going to let AZ and BZ be the sets of all integer multiples of A and B respectively. We're going to prove that if A divides B, then BZ is a subset of AZ. So, our proof will go direct. We're going to start by letting A and B be natural numbers, such that A divides B. Now, the definition of divides tells us that B will equal AK for some integer K. Now, the key part of our proof now to show that something is a subset is we're going to choose an element in this first set. So we're going to choose X to be an element of BZ. Now, the fact that X is an element of BZ tells us that X can be written as B times N for some N in Z. But what do we have from above? We also know that B is equal to AK. Thus, we can say that X is equal to Bn, but that means that we can rewrite this as AKN, which means we can write it as AKN. What do we know about Kn? It has to be an integer, because the integers are closed under multiplication. Thus, what do we know? We now get that X is a multiple of A. That means that X has to be an element of AZ. So ultimately, now we just found that our element has to be in the second set. Therefore, we can conclude that BZ is a subset of AZ. This is often called an element chasing argument because we pick one element in one set, in this case BZ, and we chase it until we find that it also lives in the second set AZ. Let's look at another one. So we're going to suppose that A, B, and C are sets, and then we will prove that if B is a subset of C, then A cross B is a subset of A cross C. So, our proof, we start by supposing that A, B, and C are sets such that B is a subset of C. Now we're ready to start chasing our elements. So the first thing we're going to do is we're going to pick our element in this first set. So we choose XY to be an element of A cross B. Remember that our Cartesian product is sets of ordered pairs, so our element that we choose in this case has to be an ordered pair. So the definition of cross product tells us that X is an element of A and Y is an element of B. Now, the fact that Y is an element of B and the fact that we know that B is a subset of C, those two things tell us that Y has to be an element of C. That's the definition of subset. So these two things together now tell me that X is an element of A and Y is an element of C. So the definition of our product again comes into play, and we can conclude that XY has to be an element of A cross C. So again, we started with something in that first set, and we conclude that it's in the second set. So we've reached the end of our proof, and we do a happy dance. Now sometimes we want to prove that two sets are equal. And doing this is like proving a biconditional. We prove that A is a subset of B, and then we also prove that B is a subset of A. So here, in the outline of the proof, you see we want to conclude that A is a subset of B. So we choose an element in A and get that it's also in B. And then for the converse, we suppose X is an element of B, we conclude that it's an element of A, and therefore B has to be a subset of A. So once we have that A is a subset of B and B is a subset of A, we know that A and B are equal sets. Now, there is a caveat. Sometimes we can string together a nice chain of equalities and definitions. So let's look at one example of that. So here, if we have A, B, and C are sets, then A minus B union C is equal to A minus B intersected with A minus C. So we need to remember what's the definition of set difference in this case. And you can start with either side of the inequality and work your way to the other side. Here, I've started with the left. So A minus B union C, the definition of set difference tells us that it's the set of all things where X is an element of A and X is not an element of B union C. So that's our definition of set difference. Then we're going to use the negation of a statement to rewrite that as X such that X is an element of A and not X is an element of B union C. So now the definition of union comes into play. Definition of union, remember, union is an or statement. So we get that X such that X is an element of A and not X is an element of B or X is an element of C. And make sure that you keep enough parentheses and that they're all paired out throughout this process. Then we use De Morgan's laws to distribute the negation across the or, which in turn changes it to an and. Then we use our definition of negation to bring in x is not an element of B and x is not an element of C. Now, as soon as you have three ands going together, we can distribute across and bring each one into a nice pair, which in turn allows us to go back to the definition of intersection. And then finally, our definition of set difference comes in one last time to get to the right-hand side of the equation. Hence, our proof is complete. So you can't do this every time you want to prove two sets are equal, but it will happen often enough that you should be aware of it and comfortable doing it. As much as anything, you have to be very careful with your definitions. Again, what's the lifeblood of a mathematician? Definitions, definitions, definitions. Make sure you know these definitions that we had earlier in the semester. They're going to be the thing that gets you through most of these proofs. That's all for now. Thanks for listening. Have a great day.